Welcome to Get Auto Care. In this video, I will explain the construction of shell type transformer. Already we have completed the construction of core type transformer. If you miss that video, please go through that video. Now, this is called yoke and it has three legs or limbs. There are two side limbs, side limb 1 and side limb 2, and one middle leg or middle limb. Let the LV number of turns of shell type transformer is 300 and HV number of turns is 400. Then what we do? This is N1. The LV number of turns N1 equal to 300. Then what we do? N1 divided by 2, that is equal to 150. Again, this N1 divided by 2 that is equal to 150 divided by 2, that is equal to 75. Therefore, LV winding is distributed in three parts: 75 plus 150 plus 75, that is equal to 300. Again, the high voltage winding N2 equal to 400 number of turns. Then now N2 by 2, that is 400 divided by 2, that is equal to 200. Now 200 plus 200 equal to 400. What we do? The LV winding by low voltage winding is divided into three parts of 75 number of turns plus 150 number of turns plus 75 number of turns. But HV winding, high voltage winding, is divided into two parts, that is equal to 200 number of turns plus 200 number of turns, total 400 number of turns. First, we place the LV winding in the near the upper yoke. That is the LV winding, and there is middle LV winding, low voltage winding, middle LV winding, then down LV winding. Upper there is a LV winding, in the bottom there is a LV winding, in the middle there is also LV winding. The upper LV winding, the number of turns is N1 by 4. In the lower LV winding, the number of turns is N1 by 4, that is equal to, here that is equal to 75, that is equal to 75. 75 plus 75. And the middle LV winding, there is number of turns of N1 by 2, that is equal to 150 number of turns. Then the high voltage winding is placed between this upper LV winding and middle LV winding of 200 number of turns, that means N2 by 2. Here we place high voltage winding again. Here we place the high voltage winding between the middle low voltage winding and lower low voltage winding. This has a number of turns of N2 by 2 and this has a number of turns of N2 by 2. Here that is equal to N2 by 2 equal to 200. Here N2 by 2 equal to 200. and this is HV winding. One point is clear, the middle LV low voltage winding has number of turns double that of upper or lower LV winding in order to get the symmetrical force. That means LV winding has 300 number of turns. If 300 N1 equal to 300, so N1 by 3 equal to 100. If we place the LV winding like this is 100, then this is 100, then this is 100, 100, 100, 100. These all are LV winding, and in between there is a high voltage HV 200 plus 200, 200 plus 200. If we do this, that means LV winding are uniformly distributed, then we get an unsymmetrical force. But if the middle LV winding is double of that of upper and lower LV winding, like this is 75, then in middle 150, in the lower also 75, and the high voltage it is 200 number of winding. Here high voltage, half of high voltage, 200 number of turns. If we do this type of configuration, then we get the symmetrical force between the winding. Here we get unsymmetrical, here we get symmetrical. Therefore, construction of shell type transformer, we do not use this configuration, we use this configuration. Whenever flux is produced, flux phi will be passing through the middle leg. This flux see two parallel path, one right side direction and that left side direction, and phi will be divided by 2, that is phi by 2 and phi by 2. This phi by 2 will circulate in this direction and returns back, and this phi by 2 circulate in this direction and returns. In the middle leg the flux is phi, and the side two legs the flux is phi by 2. Therefore, the cross section area of middle leg is double that of cross section area of side two leg. It means cross section area of middle leg equal to 2 into cross section area of side leg. Now here low voltage, high voltage, low voltage, high voltage, low voltage. This type of winding fashion is called sandwich nature of winding. It is the LV winding voltage is placed nearer to the yoke so that we require less insulating materials. The difference between core type and shell type transformer. In core type transformer, the core will be inside and outside there will be winding. We can say core is surrounded by winding. Core surrounded by winding. In shell type transformer, here outside there is a core, inside there is a winding. Therefore, winding is surrounded by core. Winding surrounded by core. Here, for passing of flux, only one but single path is there, and all over the core the flux is phi. In shell type transformer, here flux is phi. It is divided by into two parallel path, phi by 2 and phi by 2. Returns back, phi by 2 returns back here, and this phi by 2 returns back in this direction. This is phi by 2, this is phi by 2. Number 2, it is a series magnetic circuit. Here it is parallel magnetic circuit. Here the flux is phi, here also flux is phi. Therefore, cross section of two leg is same. Cross section of two legs is equal. Here in shell type transformer, the flux in the middle leg is phi, and in the outer two legs the flux is phi by 2 and phi by 2. Therefore, cross section area of middle leg equal to double of cross section area of side leg. Here the diameter of low voltage winding is D1 and diameter of high voltage winding is D2. Therefore, more copper material is required. More copper material. But in shell type transformer, the diameter of low voltage winding and high voltage winding is same, D2 equal to D1, less copper material. Less copper material. Since copper material is more required and the copper material depends upon the current rating, the core type transformer is used for low current rating. Here in the shell type transformer, we require less copper material. Therefore, we can use in high current rating transformer. This is high current rating. Point number 6. Here insulating material required will be the less insulating material. In the shell type transformer, we required more insulation. Okay, high voltage side also nearer to the leg. Here high voltage side is outside the leg, therefore less insulating material. Here both low voltage and high voltage winding is nearer to the leg, therefore more insulating material. More insulating material is required. Point number 7. Since we require less insulating material and insulating material requirement depends upon the voltage rating, therefore it can be used for high voltage application. And the shell type transformer is used for low voltage application. Point number 8. For high rating transformer, the cost of insulation will be more significant compared to cost of copper materials. Therefore, the core type transformer is used for high power rating transformer. The shell type transformer is for low power rating. Point number 9. Here in the core type transformer, the leakage flux is more. Therefore, XL will be more. Leakage flux is more. Here leakage flux is less since it is the air gap is less here. The here core is there, but one leg is there, and the middle leg, this is side leg, and this is the winding. There is no air gap. Okay, therefore leakage flux is less. Core type transformer, leakage flux phi L is more. The leakage reactance equal to 2 pi F into inductance leakage reactance is more. As a result, the voltage drop due to this leakage reactance will be high and the regulation is high, is more. Here, since leakage reactance is less, XL is less and the regulation will be less. Thank you. I am hopeful that after watching my video, we will have a clear concept of shell type transformer, and that is the difference between core type and shell type transformer. Please subscribe my channel and share to all of your friends for further notifications. Thank you once again.